Now, a number of things to talk about today, one of which relates to, very quickly relates to the homework that you just handed in that Zach gave back to you, having to do with the shoulder flexion data set. There were a bunch of different questions, and the last question I just want to reemphasize for those who might have either not gone to Zach's lab or didn't look at his lecture recording. The last one, the extra credit one, basically, extra credit, you know, what does that mean? Doesn't really mean anything, but it's harder, where nobody did it. But the question was, which is fine, it's extra credit, you didn't get extra credit, but you wouldn't have, never mind, forget it. So, but the question was, for the shoulder flexion data, when you were dealing with the model that considered subjects as an effect in addition to day and time. So you actually had three factors, day, time, and subjects. You could look at the model as a three-way ANOVA model, and I'm just talking about it right now. And if you looked at it as a three-way ANOVA model, then, and you try to set up the code to run that. Now, I'm not sure where that is. It's not here yet. It was setting it up. I guess we did it. Where is it? Here. This is the three-way model, except that technically it should be written like this. I talked about last time. Zach may have rehashed that. And if you wanted to actually see what, for that model, what the covariance structure was, or corresponding with the correlation structure, is when you go from covariances to correlation by dividing by the square root of the product of the variances. There were hard ways to do it and easier way to do it. And hard ways to do it is actually to use the matrix formula, where the matrices in the formula were the Z and the G, for example, in this formula were these two matrices, as I'm showing you here, and the R matrix was sigma square I, and to actually work through the matrix formula to get a scalar formula for what all those covariances were, with the covariance structure. Well, that most people, nobody did it, and the reason why you didn't do it, you didn't want to have to do that, and the reason why you didn't want to have to do that was because there's an easier way of doing it, just using a code statement in the program code when you're running the model. And the code statement, I don't know if I actually have it in here. Let's see if I have it. I'm trying to find it here. This would be a way you could run that model without necessarily asking the computer to give you the variance covariance structure. You will get an R matrix and a G matrix information, but you won't get the entire V matrix, which is ZG, Z prime plus R. But all you have to do to get the computer to print that out is to do what? I'm just waiting for your answer to that. What do you have to do? You have to add something to the random statement. And what do you have to add? You have to add a little statement which says vcorr, VCORR. If you add that on this line where it says subject equals subject SG, and then you add VCOR, what are you going to get? I'm just trying to ask you, what are you going to get? And in the homework, in the answers to the homework, which I think you've gotten, or at least they're on Blackboard, and the answer to the homework, you'll actually get numerically what's in that ZG, Z prime plus R matrix by putting in vcorr. You'll actually get the correlation matrix. If you put in V as opposed to vcorr, what will you get? Put in V and not vcorr. Vcorr means correlation. V means the covariance matrix. If you put that in the computer, it will automatically do that. So you don't ever have to really worry about using this formula, wherever it is, this formula to compute that for any situation, because the computer can do it for you. If you have random effects, you put in the vcorr statement, VCORR, and it'll compute it for you. So you can see what and it turns out for these data, you will see, if you looked at the homework and homework answers, or you looked at Blackboard for the homework answers, you'll see that that V matrix, or the vcorr matrix, is not exchangeable. It's something that reflects the fact that you have a three-way ANOVA problem where subjects is one of the factors in there. So it's not an exchangeable correlation structure, it's something different. I don't really have that readily to show you, but I'm just trying to emphasize the fact that there's this option called vcorr, that if you add it on this random line after the subject, after the option statement, and you add it before the semicolon, you're going to get that matrix is going to be printed out for you. It's going to do it for you. Okay, so that's one thing. Okay, now another thing I want to talk about a little bit is one of the things I did near the end of the class, not exactly at the end of the class, was I talked about ways to test for a random effect. I just want to go over that quickly. Ways to test. In other words, if your model has fixed effects and it has random effects, and you want to test for fixed effects, you use contrast statements, as I talked about earlier and illustrated in the class. If you want to test a hypothesis about whether one or more random effects are significant or should stay in the model, we're talking about what's called the random effects are the B's in the model. They're the B's, the random terms that you're adding to the fixed effects in the model. And each one of these random effects, each one of these B terms is a random variable, so it has a certain distribution, which is generally assumed to be normal, with mean 0, and it has a variance, a certain distribution, normal, mean 0, and a certain variance. And that variance of any one of those B's is called the variance component. It's called the variance component. And if you want to test whether that random effect, any one of those B's doesn't need to be in the model, what you're talking about is testing whether that variance component, which is a variance, whether that's equal to 0 or not. That's what you're testing. So if there's a random intercept, and that's the only term you have in the model, then what does the G matrix look like? It's just a random intercept. You don't have a random slope. What's the G matrix look like? What's the dimensions of the G matrix? It's a 1 by 1, and what's the value? It's a 1 by 1. It's just a single scalar number. What's in the G matrix? It's the variance component or the variance of that single random effect for the intercept. And if you want to test for the intercept, you're testing whether that variance component, or that sigma square, is equal to 0. If sigma square is equal to 0, then you don't really need a random effect for the intercept. That's the idea. And there are 3 ways to do those kinds of tests. You can also test for random slope, in addition, or before you do a random intercept. But there are 3 ways to do that test. There's method 1. I talked about the approximate LR test, where you have to consider the model that you're starting off with, which has the fixed effects and the random effects, and then you have to consider the reduced model under the null hypothesis that one or more of those random effects isn't significant. So that's the reduced model. You're dropping one of the B's, or it could be more than one B, and you're getting a likelihood ratios test comparing those 2 models. And then it turns out the sort of the extra part of this method 1, it's called an approximate Lr test. And what you have to do is you have to recognize that you're testing something about a variance. A variance can never be less than 0. So when you get that chi-square statistic, it has to be halved. The p-value has to be halved. But there's also another issue where you have to consider the degrees of freedom for that test. For method 1 is the number of variances and covariances in the G matrix that must be set equal to 0. If there's only a random intercept, there's only one sigma that has to be set equal to 0. If there's a random intercept and a random slope, then you have to set the variance component for the random slope, and you have to set the covariance for the random intercept and random slope, both of them equal to 0. That's why P is equal to 2. Okay, so that's the first thing I talked about. I'm just doing this fast here. Method 2 was the approximate Wal test, which you basically, it's a Wal test, it's a chi-square test, or it's a square of a Z statistic. It's the estimate of the variance component divided by its standard error, and if you square it, you get a chi-square statistic. And the computer program automatically will print that out if you write the code correctly, particularly putting in a word cove test. And when you do this test, you'll find out whether one or more of those random effects are significant or not. I'm trying to find where I showed you that. Somewhere over here. I can't find it now. It's not over here. No, not here yet. Guess it's, okay, here. Okay. So if you put in Cove test, you get this information and you get these Z statistics and these probabilities, and these are the things that you can use to do this large sample walled version. But that's not the best version. That's not the best test. There are three ways to do a test for random effects. First one is that Approximate Lr Test. Second one is the Wal Test. And the best one is called the, now I've got to find the darn thing again because I'm going through this thing. The second one is called the Mixture Test. And the Mixture Test is where you have to get a likelihood ratio statistic, just like you did in the Approximate Wal Test for the model that you're starting with and the model that the model reduces to under the null hypothesis. And then you get a likelihood ratio statistic, like I guess I'm not sure where it is here. There it is. You get a likelihood ratio statistic that you assume is approximately the mixture of two chi-square distributions. And then you have to somehow figure out what the p-value is for that. And one way to do that is to actually do it yourself by just writing a formula for what the p-value would be. If this is the formula for the likelihood ratio statistic, then this would be the formula for the p-value, where you'd have to get the probability or p-values for the likelihood ratio test for chi-square with 2 degrees of freedom and chi-square with 1 degree of freedom, and you'd have to sort of put that into this formula and get a p statistic, which in this case would be 0.07, and you'd find that this mixture test was not significant at the 5% level, but maybe significant at the 10% level. So that's how you do it. Now, the other way to do that is to use what's called the macro that is on the computer. And so I have that macro on Blackboard, and I'm going to just basically, at this point, if I can find it during the break, I'll show you something after the break. But what I was trying to do is show you how the macro works. And the macro is just a bunch of code that will allow you to compute this thing, to compute that p-value without having to actually go through this process. So I'm going to skip that because I can't find the macro in my notes here, in my files. So now so in any case, there are three ways to test for random effects. Okay. Now, and I can give you an example. I think actually I can give you an example of the mixture test by doing the following. I'm going to go back to one of the examples that I haven't really started talking about. I started mentioning it, the gaze angle data set. Let's see, where was it? Oh yeah, here's the gaze angle data set. Gaze angle data set. Okay, now bear with me. Okay, now we've had the shoulder flexion data set, posture measurement. Now we've got another posture measurement, gaze angle. Okay, now I introduced this example last time near the end, and in this example, in addition to day and time as two factors of interest, there were also two raters that were able to rate people on Monday and Wednesday and Friday and AM and PM of each of those days. So you had three factors, and you also had a fourth factor, subjects. So the question of interest in this case was, again, it's the same question. Does posture change over day of the week, time of day? And now there's a third issue. Does it change with rater? Does the posture measurement change depending on who the rater is? So that's another factor. And is there an interaction between day and time, day and rater, time and rater, et cetera, that type of thing. But so there are three factors here, but the problem with this one, the rater factor, is the rater factor. There were two of them. But the question was the investigator interested in those two raters as the only two raters possible, or did they look at these two raters as a sample from a larger collection of raters? Remember I mentioned that last time? So depending on the answer to that, you'd have to treat the rater factor as either fixed or random in doing the analysis. You know the day and the time factor are fixed. You'd only do the study of those 3 days of the week, Monday, Wednesday, Friday. You only do it AM and PM. But in terms of the rater factor, whether it's a fixed or a random factor depends upon whether you think you're interested in only those two raters or consider it as a sample. Now, depending upon what you decide, the code's going to be different, depending upon if you try to run this model considering subjects. So that's what I want to sort of talk about now. So I want to look at the code here. So here's some code, okay? So let's look at this now. Focus on this thing. And the code number 1 is when rater is fixed. Code number 2 is when rater is random. Rater is considered random. Now, look at the model statement in code number 1. How do you know that rater is being considered fixed? A fixed factor or a fixed, the coefficient of the rater is considered to be a fixed effect. How do you know that? Because the variable rater is actually in the model statement. If it's in the model statement, it has to be a fixed factor. Okay. Now, there's also a random statement here. Okay, there's also a random statement. It says intercept day, time, rater, day times time, day times rater, time times rater. It doesn't have day times 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 rater. We'll talk about that in a minute. So what's this doing? What is this? See, this part of the model is talking about, well, what the fixed effects are. Now, this part of the model is putting in random effects. So what are the random effects? Well, there's a random intercept, right? A random intercept for subjects. There's a random interaction term of what? Subjects with day. There's a random subjects by time. There's a random subjects by rater. There's a random subjects by day. Why are all these terms random factors in this random statement? Because the statement says random, okay? And it says subject equals subject. Well, if you fit this model, you're effectively, I don't know if I actually written the model out up here. Did I actually write the model? I didn't write the model. If you fit this model, rater's fixed, and you're allowing for the possible, you're allowing for treating subjects as a random factor, even though rater is considered to be a fixed factor. So you're allowing for interactions of subjects by day, subjects by time, subjects by rater, subjects by rater times time, so on. That's what this is doing. Well, how is this different? Number 2. How's number 2 different from the first one? What don't you see in the model statement? You don't see rater in the model statement, correct? Why isn't it in the model statement? Because this is a code, not necessarily the code. This is a code you could use to tell ProcMix to fit this model if you want to consider rater to be a random factor. Okay, that means you're assuming that those two raters were sampled from a larger collection of raters. Now, it turns out, I mentioned this the last time briefly, in the actual study, Michelle Marcus, who did the study, said those are the only two raters that we were dealing with. So we only wanted to draw conclusions about those two raters. So really, the first model was better than the second model. But you know, if you wanted to argue that maybe it wasn't, or if you wanted to consider the fact maybe they were sampled, then this would be the model. Now, how do you know this is treating rater as a random effect? Well, but something's tricky about this model. What do you notice is tricky about this model? There's the model statement, but there's two random statements here. Not one, two. Okay? Why are there two random statements? Well, look at the bottom one, the one in blue. It says random rater times day, rater times time, rater times day times /SG. It's treating all these variables in here as random effects. Okay? But how do you know that this is rater and not rater times subject? How do you know this is talking about rater as a random effect and not the interaction of rater with subject? How do you know that? Because to the right of the option statement, it doesn't say subject equal SUBJ. If it said that, then whatever you wrote there on the left would be interaction of rater with subject. But that's not there. So this model is allowing for rater to be in there as a random effect. Rater times day is. Why would rater times day also be a random effect if rater's in there as a random effect? Because it's a product of two things, one of which is a random effect. So that every one of these things have to be a random effect because it's allowing rater to be a random. So what are these things? What's this? Why is this in the model? Well, what is essentially where it says random intercept? What's that? That's the random intercept for subjects. Okay, for subjects, not for rater, for subjects. And this is subjects by day, subjects by time, subjects by rater, where rater is in here as a random effect, but this is the interaction of subjects by rater. This is just rater. This is subjects by rater. Subjects by day times time. Subjects by day, that's what's in here. So effectively, this second code is what you'd have to use if you wanted to treat rater as a random effect. Now, I'm not sure, do you get that? I mean, there's a difference here. The thing that you have to do is, if it's a random effect, you can't put rater in the model statement. You could put rater in a random statement, but you got to separate out rater here. Now, this is not the only way to do this, because I'm going to show you another slide here. Okay, this is, now, again, I've shown you rater fixed, rater random. Now I'm taking the rater random, the one at the bottom, and I'm moving it to the top here. That's the one I just looked at. And down below it, I'm showing you an alternative way I could write the code. The alternative way I can write the code to do exactly the same thing. Can you tell me what's there? How many random statements are in the alternative code? 2 or 1? 1. Why is it 1? Because what I'm doing is I'm trying to avoid having 2 statements with a subject equal SUBJ. I'm trying to use just one statement, one random statement that considers all the random effects in one statement. So this says random subjects, subjects by day, subjects by time. And you notice to the right of the option sign, of the option, the slash sign, there's no subject equal SUBJ. So, for example, you see raters in this statement. Well, rater's in the statement, there's no subject equal SUBJ, so this is rater as a random effect. So this second code is equivalent to the first code. Now, I'm not telling you which way to do it, I'm saying there are 2 alternative ways to do it. So you may have to figure this thing out for whatever situation you have for your project. So that's how you would do that. Now, it turns out that, see this list over here? This list over here? This is sort of what you're going to have to do in your homework assignment for next week, the third question. Because what I did was, you see this thing number 2, it says repeated measures ANOVA rater random. One of the things you're being asked to do for the homework assignment for next week is to take this gaze angle data set and assume rater's fixed, run the model. Assume rater's random, run the model, and get some estimates and draw some conclusions about whether there's an effect of day, time, and rater or their interaction. Okay. Now, you notice that it turns out I'm only showing you what happens when you consider rater as random. So if you look at this, the very top set of statements here, the very top set of statements, this is the statement I already showed you. As number 2. This is the top here where I'm actually using 2 random statements. I think that's what this says here, 2 random statements. So this is the thing I would say, if I want to treat rater as random, these are the set of statements I would put into the proc mix and run the model. Well, it turns out when you run the model, this is what you're going to find out. This is what I want you to find out. When you run the model, you're going to get an error message. And it's going to say, can't run the model. Something wrong with this model. So what you'd like to do, you can't do. And this is what happens all the time. Not all the time. This could happen in any project you're doing where you try to run something that, in this case, I'm trying to consider this general, what do you call it, ANOVA model, treating these 4 variables as factors, and it doesn't work. So what did I do here? Look at model 3. What's model 3? This is where what happens, now you remember, you guys know that I play music and I improvise. This is where you have to improvise, okay? Or you have to do an ad hoc procedure. You have to do something to try to get around the fact that this model won't work. I can't do it the way I want to. I want to get something to work so I can evaluate the effect of day, time, rater, and any of the interactions I want to. So what did this model do? What did this model 3 do? Well, I dropped something. I want to see, well, the other one didn't work. Let's do the following. Let's drop, what did I drop? I dropped rated times day times time. I dropped one of them. I dropped this three-way product term. Isn't that what I did to get that? Okay. Turns out when I do that, it doesn't work. That doesn't work. So that's no good. So again, I have to improvise. I get out my flute and I improvise, right? So what have I done here? What have I done here? Number 4. Well, I've dropped everything but random rater. Now you notice model number 4 still does something that I want. It doesn't do everything I want to do, but it will give me estimates of the effect of day, time, day times time, day times rater, time times rater, rater times day times time, but it'll only give me the main effect of rater. It won't give me this is subjects by, this is subjects by day by rater. This is subjects by rater. But it only gives me rater. It doesn't give me rater times time. It doesn't give me, which is one of these things, a rater times day. So I can't get the interactions involving rater, but at least I can get something for whether rater is significant if I do this. Well, it turns out this doesn't work. This is what this is something that you're going to face. You might face. And if you face it, you're going to say, I give up. That's it. I'm going to be a taxi driver. I said that last semester. Okay, then here's another thing. What did I do in number 5? What did I do in number 5? Well, I compromised the other way. Okay, what I did is I said, well, let's drop these interaction terms. Let's drop the interaction terms involving subjects over here, and let's keep it simpler. And let's leave what I originally dropped here to get this here. That doesn't work either. Okay, and then I kept going, kept trying everything. And the only thing that would work was this. It's the only thing that would work. So what am I doing? What do I get? Well, I'm going to get something about the significance of day, time, the interaction of day times time, and I'm also going to get, if I do a test for rater, the significance of rater, but I'm not going to get any interactions with rater, or with rater or rater times day or anything like that, because I only have rater in there as a random. And is this a legitimate thing? Is this a legitimate code? Well, I put random rater. I didn't put subject equals. So this is rater. And this is the one that'll work. And this is what I want you to kind of walk through for the homework assignment. Well, you may decide, I'm not going to walk through, I'll trust you. But until you see it, you don't know, that's what I want you to do, and get the output and demonstrate to yourself that this doesn't work, okay? So this is the type of thing you have to do, okay? Now, it turns out, this is rater. Now, look at the, up here on the screen here, you see what I've got in red? See the code I've written for random? That's the same code as what I wrote here. So I'm showing you the output for this model. Showing you the output for this model. Now you notice that the output for this model, among the output for this model, you see down at the bottom it says type 3 test fixed effects. So from this output, I can test whether day, time, or day times time is significant. The day, time, and their interaction. I can also assess whether rater is significant somehow. How can I do that? From what you see in the output. Well, it's not the only way to do it, but this is what I can do for this. For this thing, what information is given that would allow me to evaluate whether rater is significant or not? Where? It's up on the top here, which says covariance parameter estimates. You see the 0.2501? That's the Wal statistic, which is not the best way to do it, but it's the Wal statistic for testing whether the rater as a random effect is significant. It's not the best one, but what do you conclude from that? Not significant. So it suggests maybe, if you wanted to see whether day was significant and time was significant, it turns out that nothing is significant, which is what was the goal of the investigators, was to try to evaluate whether posture, gaze angle posture varies with day, time, or rater. It looks like it doesn't vary at all. This is the best you can do. Because if you try to do the bigger model, it doesn't work. Are you following me? I'm trying to walk you through how you would do something like, questions about this? Now I even have some more examples. This was the FEV example with two groups. So I want to talk about that. Because I already met with a couple of teams and they have similar questions. They have two groups they're comparing. And they want to see if the two groups, if they want to compare how changes over time look for each of the groups. So in this case, we had two locations in the same city, 40 school children examined under normal conditions, and then another 4 weeks. And one of the locations was within the neighborhood of the source, and the other one was located 10 miles away. So we have two groups of 40 kids. So we have a total of 80 kids, and we want to compare what's happening with the two groups. We want to see if there's a change in one group that's different from a change in another group. Now, so when you consider the model that corresponds to this, now there's the scalar model and there's the matrix model. Just look at the scalar model. Look at the scalar model. I showed you this last time. Okay, what's in the scalar model? I'm repeating, but I don't think it hurts to repeat. You notice there are 4 t variables in there. What do they reflect? 4 dummy variables for the 5 weeks, right? What does the G variable reflect? What, the location. And what does the GT variables represent? Interaction of location with time, okay? That's what this model does. So if you want to, for example, test whether there's any interaction, what would be the null hypothesis? Any chunk test for interaction. That beta 6, beta 7, beta 8, and beta 9 were all equal to 0, right? That's what you'd be testing. How would you do that test? It's correlated data because you've got repeated measures on everybody in here. And all 80 kids have got repeated measures. How would you do that test? Using proc mix, just roughly how would you do it without writing the code? How would you do it? What kind of a statement you would use? You would use I didn't hear you. What kind of a statement? A model statement? A random statement? What kind of a statement would you use to test whether there's this chunk test for interaction? It's called a contrast statement. That's what you'd use. A contrast statement, and you'd put each one of these variables with then you'd have a 1 comma, next variable, a 1 comma, and so on. That's what you'd have to do to test that. Okay. Now, it turns out, for this model, you can actually show what's going on, actually. And I also talked about this. For this model, for example, if somebody is in location 0, if location 0 is the situation where, if that was the referent group, location 0, sorry, the referent group is week 5, but if you're talking about location 0 where you're allowing, let's see, okay, let me see, location 0 at week, for location 0, G is 0, okay? So for location 0, if you want to say, well, what does this model look like for location 0? It looks like every one of these terms, beta 5G, every one of these other terms would drop out, right? Because G is equal to 0. See that? Now, what if you're talking about week 5? Week 5, which is the referent group that we've been using. You're going to have to try week 1, not for this example, but for week 5, it's the referent group. What happens to beta 1 through beta 4? They drop out also, because for week 5, T1, T2, T3, and T4 are all 0, correct? So when G is equal to 0, when G is equal to 0, you wind up getting these terms drop out, all these terms drop out, and the G term drops out, and you're left with just this. Sorry, now wait a second. That's what the model looks like when G is equal to 0, but when you're talking about at referent group at week 1, let me say it. At week 1, sorry, let's go back. At week 5, I'm getting you confused here. At week 5, all the T's are 0, and if you're talking about location 0, all the G's are 0. So you wind up at week 5, this model simplifies to beta 0 at week 5. You agree with me? At week 5, this model, everything drops out except beta 0. And you're talking about week 5 for location 0. So that's what the mean for location 0 at week 5 is. If you're talking about the mean at location 1 for week 5, then something else doesn't drop out what did I say? The mean at U5 1, location 0, at location 1. Well, location 1, the G is 1. Location 1, G is 1, right? Location 1, G is 1. But if we're talking about week 5, all of these product terms are 0 still. G is 1, all these product terms are 0, and if you're talking about week 5, all these terms are 0. So this model simplifies at week 1 to beta 0 plus beta 5. And if you've already decided that beta 0 has to be mu 5.0, then beta 5 has to be mu 5.1 minus mu 5.0. And you can solve for every one of these things by just playing with this thing. Now, I've got the solutions over here. I've got the solutions for every one of these different coefficients. I've got it for beta 5. You see mu 5.1 minus mu 5.0? I can solve for all these things. Okay. So I can actually see what I'm estimating when I do that. But let's go on with this example. Again, if I want to test for interaction, that's the null hypothesis. Beta 6, beta 7, beta 8, and then 9 equals 0. And the model reduces to this model. If you're only testing for interaction, but you're not testing whether the locations are different, that's the model you get. Okay. Is the interaction significant? Well, that's what that would be the picture if the interaction was not significant. If the interaction was not significant, then you'd be saying that the two lines, the trends over time for the two lines are parallel. But turns out when you actually plot it, this is what you get. I showed you this last time. So it looks like you might expect, even though you have to do a test, that the interaction might be significant. And so that's what you get when you actually run the data. Although the two locations start off the same, the change in mean FEV from weeks 1 to 5 are different for the two locations. There is greater decrease in mean FEV location 1 than in location 0 over the 5 weeks. So that's what this is saying. It suggests there's interaction. So how would you actually run this thing? Well, now I'm going to get out of this. Here we go. For this example, I'm just showing you all this. Showing you all this. Showing you this. Showing you this. Showing you this. This is what the data looks like. Okay. Here's the output. Here's the output when you test whether beta 6 equal beta 7 equal beta 8 equal beta 9 is 0. Look at the code. Look at the code. What model is being run here? You see it says model FEV, weak group, weak star group. What model is being run? Can you tell what model is being run? What are the variables in this model? This is what I'm asking here. What are the variables in this? And based on the code, what's the variable? You see, weak is a class variable. Weak is a class variable, right? So what's going on here for weak? 4 dummy variables for the 5 week. What's the reference group? Week 5, because that's the way it works in proc mixed. Okay, group is not defined as a class variable. It doesn't need to be because it's a 0-1 variable. It's a binary variable. Okay. Then I've got weak times group. So what's that? What's weak times group? What's that? Is that one variable? No, it's not. It's one variable, but it involves how many real variables? It involves group times weak times T1, group times T2, group times, so this involves the 4 product terms. Can you see that? This involves the 4 product terms. So what I'm doing is running that model, running that model, this model has the 4 T's, it has the 4 GT's, it has G in there. I'm using proc mix to run this model. There it is. Okay. So now you notice, for example, that at the bottom of the slide, see at the bottom of the slide, you see it says type 3 tests of fixed effects, and you say group star weak 4, 390, 19.74. What's that doing? What's that testing? What's it testing? Whether there's significant interaction. It's testing whether the 4 variables for group times week, those 4 variables taken collectively are significantly different. Whether delta 6 equal delta 7 equal delta 8 equal delta 9 equals 0. That's what's being tested. That's what this is testing. Okay. Now, why did it automatically come out? You notice I didn't use a contrast statement. To do this, I got a test. This is the code I used, but I didn't use a contrast statement. Why did I get this test? Why did it automatically come out? Because I put this interaction term in the model using a class statement. So the program, the proc mix, will automatically test for this group interaction thing because it had week in there as a class variable. So I'm getting this thing, I don't need a contrast statement. Now, if it turned out I defined 4 dummy variables for the 5 weeks, suppose I did that, 4 dummy variables for the 5 weeks, how would things differ? Well, I wouldn't necessarily have a week variable in the class statement. What would I have in the model statement? I wouldn't have week, I'd have 4 W1, W2, W3, W4, and then I'd have 4 group times W1, group times W2, group times W3, group times W4. And if I tried to run that model, I could run that model. If I ran that model, I wouldn't get this test unless I did the other way, unless I used a contrast statement that had those 4 things separated by 1s. Week 1 times G, space 1. Week 2 times G, space 2, comma, separated by commas. So I'm just trying to say, this is how you do it. But what does this say? It says, this is a result that says this is significant. So it looks like I have to assume what I saw here is that the effect of, if I want to compare what's going on in the 2 locations over time, I'm drawing the conclusion that the trends are different and there's interaction. That's what I'm concluding from it. And in a way, I'm sort of done because I could actually do it. Now, look, for example, look at this code. Look at this code. Let's see what did I do here? Look at where it says model FEV week 1, week 2, week 3, week 4. See that? It says group. And it says G week 1, G week 2, G week 3, G week 4. So that's the way I would do the analysis if I wanted to use it with dummy variables. Now, but the problem is, if I wanted to test for the interaction, I'd have to use this test. Contrast, compare, and then I would say G times week 1. Well, actually, that would not be the, that would be the estimate of 1 versus the other 4. If I actually wanted to this would actually not be doing that chunk test. In order to do the chunk test, I'd have to write a contrast statement, and I'd have to have G1, 1, comma, G2, GWK2, comma, and 1, space 1. I'd have to actually add to this model. Let me do it. Suppose I wrote this. Contrast interaction. Then I wrote GWK, 1, space 1, comma. What would I do next? GWK2, 1, comma. GWK3, 1, comma, GWK4, 1, home. Okay, so let's go back to U, Zoom, 66, boom. Look look at what I've added to this thing. See contrast, interaction, GWK1, 1, GWK2, 1, comma, 3. What is this testing? It's testing all the interaction. So what's this doing? What's this estimate doing? What's this doing? It's a little tricky. What's this doing? Is it a contrast? Is it a test? No, it's an estimate. What is it estimating? Well, it's estimating something. Now, GWK1 is the first interaction, beta 6. That's the coefficient of beta 6. And this is the coefficient of beta 7, beta 8, and beta 9, beta 6, sorry, beta 6, beta 7, beta 8, and beta 9. So what is this doing? It's beta 6 minus the sum of beta 7 plus 8 plus 9 over 4. Well, what's that testing? Well, what it's testing is somewhere over here. It's testing, it's estimating. Let's see if I can find the estimate. Is it estimating? Oh, there it is. Down here, see where it says contrast, compare? You see this code that I've added this. You see it says contrast, compare? Okay, now wait a second. Oh, okay. See where it says estimate, contrast, compare? And then it's got this. This information, this 2.0718, what is it? Can anybody tell me what that is? Is that the answer that I get from this statement or from this statement? It's got two statements here. This is contrast interaction. This is contrast this. You see the 2.0718? What is it comparing? It's comparing whether the interaction is comparing beta 6 minus beta 7 minus beta 8, beta 9. It's comparing group 0 with group 1. It's comparing whether the interaction for group 0 is different from the interaction for group 1. My goal here was to basically say that if you were looking at these data and you wanted to test whether there was significant interaction, that test will do it. It says there's significant interaction. Okay. Now it turns out that the other thing, if you want to say, well, let's suppose I want to see whether group 1 treat the difference between week 1 and the other 4 weeks for location 0 was different than the week 1 and the average of the other 4 weeks for week 1. That would be the second test. That's the second test that I'm doing. I don't know if I'm explaining this. This 2.0718, what that's actually testing, and that's what this is testing, it's comparing whether what happened, what overall, whether the difference between week 1 and the other 4 weeks is different for location 0 than it is for location 1. That's what this is actually testing. And it turns out it's saying that it's highly significant. Okay? It says if you're asking about whether what happened from the first to the other weeks for location 0, you're saying location 0 and location 1 were very different. That's another way of saying interaction. It's another way of saying that what happened in location 1 through the other 4 weeks, week 1 versus the other 4 weeks, and location 0, week 1 versus the other 4 weeks, were different, and that's what this thing is testing. So you can do all this, and I've totally haven't made it very clear, but I'm going to stop here because the point here is the point of the whole example is that you can do this FEV thing, and you can use proc mix to compare 2 groups. And if you have 2 groups, then you're talking about a model where you have to worry about interaction, and that's the model we're dealing with. That's the model. That's the model we have to worry about. And if you've got a situation like that, as some of you have, that's the kind of model you're working with. And you can test for interaction, and you can test for whether interaction is different for the 2 groups that you're comparing, and do a whole bunch of different tests. So I'm going to stop with that. And then I'm going to do, let's see, I got one other thing I want to do before we take a break. And this is going to be easy. This should be easy. This is going to be clearer if I can find it. Here's a model. Okay. This is a shoulder flexion model, okay? You notice that the model has got 2 dummy variables for day, a dummy variable for time, and 2 product terms. And then it's got a program code, and it's got some questions. See if you can answer these questions. First question is, here's the program code. Is this a marginal, random effects, or conditional model? That's the first question. Marginal, random effects, this is easy. It's confusing, but this is marginal. Why? You see a repeated statement, and you don't see a random statement. Okay? What are the R matrix? What's the R matrix? Given the code. This is easy, right? What's the R matrix? Compound symmetric. What's the G matrix? 0. There's no G matrix. Will the output automatically provide a test for the day times time interaction? Will it automatically provide it, or do you have to use a contrast statement to do it? That's what I'm asking. Will it automatically define it because you've used a class statement to define day and time? That's that question. Okay. What is the distribution of the test statistic for the interaction test, including the numerator and the denominator degrees of freedom? What's the distribution? Distribution of the test statistic for the interaction test. It's a F statistic, okay? What's the numerator degrees of freedom? This is a test for, what are we testing? Interaction. The numerator degrees of freedom is 2. What's the denominator degrees of freedom? Remember, it's a marginal model. So what should the denominator degrees of freedom be? N minus the number of parameters in the model, whatever that is. And the number of parameters 1, 2, 3, 4, 5, 6. So it's N minus 6, and it's 19 times 6, which is 114 minus 6. I guess it's 108 is what it should be. Okay, so there are the numbers. Okay, what does the why does the code use that? Why does the code say DDFM equal residual? Why doesn't it say contain or something else? We talked about this last time. I'm reviewing the last time. Why does it say DD? Because the model is a marginal model. When the model is a marginal model, regardless of what the correlation structure is, the typical thing that people do is you use the residual. Because you're not taking something out for random effects. You don't have any random effects. You're not removing random effect degrees of freedom. Okay? How would you change the code to obtain empirical or robust estimators? How would you change what's written here? What would you do? You'd add something. That was question, I guess, E on the homework. What would you add? You'd add the word empirical. Where would you add it? At the top, on the top line. I don't even think it needs a slash. It's just empirical. You write data equal to SF space empirical. Got it? Okay. Why is subject equal to SUBJ and vcorr included in the repeated statement? Why is subject equal to SUBJ included in the repeated statement? Because if you don't put it in, it's not going to deal with correlated data. You have to have the cluster. That's telling the computer what the cluster is. Okay? Well, what's vcorr doing? What's vcorr asking the computer to do? It's giving you what output? The estimated R matrix, which is, in this model, it's compound symmetric. vcorr, the estimate, actually is giving you the estimated R matrix for the first person in the data set. So if there's unbalanced data, it's only going to give you for the first person. First person has 6 observations. It'll be, well, the first person does in this case. And there are the answers to this. These are all the answers to what I just talked about. Okay. Now, I'm still going to go on here, and then we're going to take a break. Okay, here's another model. Okay. Different program code. Is it a different program code? Look at the program code in this model. What do you notice? There's the model. It's the same model as before. Different program code. Is it a marginal, random effects, or conditional model, and what are the R and G matrices? It's a marginal model, just like the other one. not a conditional or random effects model. The R matrix is compound symmetric, and there's no G matrix, right? Okay. Will the output automatically provide a test for the day times time interaction? No, why not? Because they're in there as two separate terms, so you'd have to put some contrast statement with each term with a space and a 1 and a comma. That's what you'd have to do that. How would you write the contrast statement to test for day times time interaction? Well, there it is down here at the bottom. There's the contrast statement. See that? Maybe this is helping, because this is it's reviewing just about everything we've done. The other stuff maybe was getting complicated. More questions? Okay. Now, this model only has the day variable in there. It doesn't have the time variable in there. Okay. And here's the program code again. Will the output automatically provide a test for day? The output automatically provide a test for day. And here's the output. The answer is yes or no. In other words, do you need a contrast statement if you wanted to do a test for day, which is there are 3 days, So the answer is no. It won't automatically, because you're going to have to put a contrast statement. Do you agree with that? You're going to have to put a contrast statement. How would you write the contrast? Well, let's look at the next page. No, the contrast statement would be D1, 1, comma, D2, 1, colon. That's the contrast statement for day. Okay. Are you with me with this? How would you write the contrast statement to compare Monday shoulder flexion scores with the average of Wednesday and Friday shoulder flexion scores? There's the answer. Why? That's the answer. And this next question, how would you write an estimate statement to allow you to obtain a 95% confidence interval that it compares Monday shoulder flexion with average? Look at this over here. Where did that come from? This was Monday. Remember, there's 3 days. Monday, Wednesday, and Friday. Well, look over here at the top. Over here, look at this model. Now, for this model, the code, the reference group is day 3. Okay, the reference group is day 3. So, day 3. The reference group is, what did I say? Beta 0 equal F. Friday. Sorry, day 3 is Friday. Right. So this is so beta 0 is the mean for Friday. Beta 1 is Monday minus Friday. Beta 2 is Wednesday minus Friday. So if you want to ask the question, is there a difference between Monday and the average of Wednesday and Friday? What you're going to do is you're going to say, okay, here's the effect of, let's put it this way. Beta 1 minus 0.5 beta 2 is the effect of Monday versus Friday minus Monday. This is the effect of Monday. The effect of Monday, and this is minus 0.5 Wednesday minus Friday. It turns out to be Monday minus mean for Friday minus, it turns out to be, that's, if you do a little algebra with it, you see what you wind up getting? This turns out to be the mean for Monday minus half the mean of Wednesday and Friday. That's why this works, even though you might say it doesn't look like it, but if you go backwards from this, that's why it works. Okay. And so that's why you would write the contrast statement this way, and you would write the estimate statement this way. The only difference is I'm doing the same thing. I'm comparing Monday versus the average of Wednesday and Friday, but in this case I'm testing, and in this case I'm estimating. That's what I'm doing there. And it turns out that, let's see, let's see some more questions, and then I'm going to break. So we just did. Will this output automatically provide a test for day? Here's the model, no time variable in there, but you notice days in there is a class variable? Will this output automatically provide a test for day? Yeah, you don't need a contrast statement. How would you write a contrast statement to compare Monday shoulder flexion scores with the average of Wednesday and Friday scores? A little bit more complicated because it's a different model. In fact, the answer is 1 minus 0.5 minus 0.5. And the reason is you notice Monday minus 0.5, the average of Wednesday and Friday. And if I go to the left, I eventually get back to beta 1 minus 0.5 beta 2. So it turns out that, okay, what does that do? Oh yeah, because I'm now putting in the word day, so it's Monday minus 0.5, Wednesday minus 0.5, Friday. That's why that's it, and that's why that has to work. So anyhow, these are the kind of questions you got to become familiar with, or I think that helps you to become familiar with. So after the break, we're gonna take a 15, definitely need a 15-minute break. Okay, let's go back to what I couldn't find. Now I found it. I don't know if I can explain it well, but so what, and this actually refers to how you might continue to answer problem 3 for the homework assignment next time. So just because I'm showing you this doesn't mean that you shouldn't do it to see for yourselves how it works. So what I'm going to do is show you how to use the macro to do the mixture test, okay? And this is for the gaze angle data set. And if you remember, we were talking about whether the rater variable was going to be considered either fixed or random. And when we decided, if we decided to look at you have to do both for the homework assignment, but if you're focusing on rater as random, and you start out with a model that you'd like to do, it doesn't work. Remember, I went through that. It doesn't work. The model that you'd like to do doesn't work, so you try a whole bunch of different models, and the only model that worked was this one, this model. Actually, it says rater 1, could have just as easily been rater, but that's rater 1. This is the model that, this is the only model dealing with the gaze angle data set, Y is gaze angle, that worked, okay? Now, by the way, you notice that the DDFM is no longer residual. The reason why it's contained is because we're using random effects. And it's an ANOVA situation with random effects. So that's why we're using contain as the residual. So now, here's the issue. We got 2 random effects in this model. What are the 2 random effects? There's a random effect for rater, right? And there's a random effect for subjects. Is that right? Are those the only 2 random effects? Or is there anything else? It's random intercept for subjects and a random effect for rater. Okay. So if we want to do this mixture test, what we have to do is start with this model that we run it using this code, we run this model, and then depending upon what we wanted to test for a random effect or not, we'd run a reduced model. So if we wanted to test whether the rater random effect needed to be in the model, whether it was significant or not, what would the reduced model look like? How would the reduced model differ from this? What about the code for the reduced model? If you wanted to test for the significance of the rater effect in this model that has the intercept for subjects and the rater effect, the reduced model wouldn't have what in it? Wouldn't have this last line in it, right? It'd just have the intercept in there. It wouldn't have the rater, wouldn't have the slope for rater, or it's now rater's a random effect. So you'd have these 2 models. One is the full model with intercept and rater, and one is the reduced model, which didn't have rater in there. Now, on the other hand, if you wanted to test for whether the intercept effect was significant, allowing for the rater random effect to be in the model, you would start with this model, but what would the reduced model be? What would the reduced model have? What would you drop out of from this code, what would you drop out of the reduced model, drop out of this full model to get the reduced model? you drop this line, the random intercept line, to get a likelihood ratio test for the mixture thing. So let's see how that would work. Do you follow what I'm saying? So in order to run a macro, you have to include a statement to run the macro. And here's the, now, I think this should have been S, because the macro is in the S drive. But that's the name of the macro. Okay. So what I'm now doing is, I've got star full model. I'm just telling what I'm running, telling the computer what I'm running. And then I'm running this full model. Okay. Now, you notice where it says reduced model. I'm just telling the computer what I'm writing here. But notice the reduced model, what doesn't it have? It doesn't have the rater line, right? So what am I testing here? I'm testing whether there's a significant effect of the rater variable in this model, which is one of the things, the main thing I want to do, because in a way, I don't really, I mean, the intercept is fine, but the rater is one of the key variables. There's day, time, and rater. Okay, day and time are in the model. Okay, so now in order to do this, I have to put in, before I even start the full model, I have to tell the computer where the macro is located. This should be S. And then what I have to do is tell the computer to run the macro. Okay, and when you do that, you put %LR mixture test, because that's the name of it, and then you put in what you have to tell the computer. Full model, that's what we've called, I'm calling it full model, and reduced model, I'm calling it reduced model. I could call this full model Kevin, reduced model Jake, because they're sitting next to each other, right? But, I noticed that, so I could have done that, but I have to have full model on the left, and, the left side of the equal sign has to be full model and reduced model. What I put on the right is up to me. Okay. So now, here's what happens when I do this. Okay. It says full model using variance components correlation structure. Now you see this. Now what's this information giving me? And you've seen this before. This information on the screen here. What's this? This is the Wal test information. You already saw that. The Wal test for rater 1 was not significant. Wal test for intercept was significant, right? Okay. Now what will happen if we use the mixture test? Well, it turns out that if we want to test what I'm actually doing here, where I'm testing for rater now, because the reduced model doesn't have rater in it. If I want to test for that and I put in this macro, what I get is the likelihood ratio statistic is 16.485, or 16.4858. That's the LR. That's going into that formula. That's the mixture formula. And then the computer computes the p-value using the formula. It's just built into the computer program, and the p-value is 0.0002. That's what the p-value is for the significance of the rater variable. Okay. And but you notice that the Wal test is, if you divide by 2, which you have to do because the sigma, you're testing about a sigma, and the sigma can't be less than 0. You have to divide the p-value by 2. You get 0.12. And for the Wal test, for the mixture test, you're going 0.0002. So what do you notice about the mixture test versus the Wal test? You don't have the same conclusion, right? The mixture test is saying you better keep rater in there. Rater is significant. It's a significant effect. You better keep it in there, and it's significant. If you do the Wal test, you find that the rater is not significant. Okay. Now, so what am I telling you? Then what should you do based on the fact that they gave you different results? What should you do? The Wal test or the mixture test? Which one should you do? Well, you do the one you want? No. You do the mixture test because theoretically that's been shown to be the better test. If you get different answers, you use the mixture test. That's why it's, and you're going to find the rater is significant. Okay. Now, you notice that I haven't done the test for the intercept here. What if I want to do the test for the intercept? You follow me so far with this thing? It's not that hard because all you have to do you have to tell the computer with an S over here where the macro is, and then you have to write the full and reduced model, and then you have to give it a name for it. and the computer will run it for you. Okay, so, okay, so now let's look at, so using the Wal test, we would not consider the random rater term significant and would drop it. Using the mixture test, the p-value would conclude we keep rater as a random effect in the model as it is highly statistically significant. You with me on that? That's what we've just done. Okay. So now let's suppose we want to assess whether the intercept is significant given that we're going to keep rater in the model. Okay. So the full model has them both in there. Okay, the reduced model is I'm now dropping the random intercept line. That's what I'm doing to do the full model. And then I'm using this, that's the telling the computer where it's located, and that's running the model. And when I run the model, look what I get. For the intercept, the Wal statistic, highly significant. What about the likelihood ratio statistic? Also highly significant. So it turns out the intercept test gives me the same conclusion, whether I'm doing the mixture test, and it seems to say I got to keep a random intercept in there. Okay. So what do we conclude from all this? Using both the Wal and the mixture method p-values conclude keep the random intercept for each subject in the model. And it looks like based on the mixture test we have to keep the rater in the model. So that's it. I mean that's how you use this macro. So you don't have to compute it. The macro will compute this thing, but it's not that hard to compute. I mean, I showed you how it was computed with an example, but this is, you can get the computer to do it for you. You got that? So that's how you do the mixture test. It's the best test because theoretically it's got the best theoretical features. And if it gives you a different answer than the Wal test, which you often would like to do because it's easier, you're in trouble. You're potentially in trouble. Okay? So that part, at least, I think I explained. Okay, now let me say a couple of other things. So any questions about this? Okay. Now I'm looking at the time here because I want to make sure our group gets to talk about it. Now I want to say one other thing, a couple of other things. I want to show you this. This is a file in there. It's called the Appendix File. Just want to show you what this, talk about what this is. If you use mixed, or if you use glim-mix, you have an incredible wide variety of choices for either the R or the G matrix. Okay? It's either the R or the G matrix. You could choose a G matrix that's, if you have a 3x3 G matrix, you can make the G matrix AR1 or exchangeable. You can do that for the G matrix also. Okay, and this is the appendix, this appendix, which you can look at when you're looking at mixed, and you want to, you're going through the syntax, you can see what all these different things are, and I'm just showing you what these different things are. So this is a whole, you see where it says AR1? That's one of the choices. You see it says ARH1, stands for heterogeneous AR1. Remember I talked about that? Heterogeneous AR1 is where you allow for the variances to be different. The other one is homogeneous AR1. Okay. And there's all these other ones, compound symmetric, heterogeneous compound symmetric, and there's a whole bunch of other ones. Toplets, and we're going to see that a little bit later because there's another synonym for toplets, and that's called stationary. Toplets is something that we're going to talk about later. It could be used for proc mix. It's stationary. It's an alternative to autoregressive, and we'll talk about that when we get to it. But actually, this is a whole listing of things, many different things. Okay, and there's even something here. You see this thing called the direct product. This thing called the direct product. Well, the direct product, and it's got a number of different choices you could use. The direct product is a way you can specify a correlation structure or covariance structure when you've got a complicated covariance structure situation. You remember when I talked about the bypass study? Bypass study where you had a bunch of people were getting bypasses. And some people might have had 3 bypasses, 5 bypasses, whatever, different numbers of bypasses. Okay? And what was done with that study, well, one version of the study was 1 year later after the bypass, you went to look at the arteries to see if they were blocked or not. So if somebody had 3 bypasses, you'd have the outcome was either 0 or 1, depending upon whether the artery was blocked. So if somebody had 3 bypasses, you'd have 3 0, 1 values. Somebody had 5, you'd have 5 0, 1 values, which could be different. So that was one thing. But I also described the second version of that, a more complicated version, where they looked at the bypasses, whether they were blocked or unblocked, not only at 1 year, but at 6 months. Remember I was talking about that? You looked at it 1 year and at 6 months. So if you had 3 bypasses, and you're looking at whether they're bypassed at 6 months, and they're also whether they're bypassed at 1 year, what's your for that cluster, for that person? Let's say you have somebody who has 3. For that person, that particular cluster, what does the y variable look like? How many terms are in the y variable? 3 or 6? There were 6 correlated terms. The 3 at 6 months and the 3 at 1 year. They were all correlated because they were all in the same person, right? You get what I'm saying? If somebody had 5 bypasses at 6 months, you'd look at what's happening on the 5 bypasses, 0, 1, blocked or unblocked, and then you look at 1 year. So you'd have 10 observations for that cluster, for that person. Okay. So what's the correlation structure in that situation? Well, you can argue that if you're only looking at 1 year and not looking at the half year, the correlation structure, a good argument would be that it's exchangeable because it's not correlated, it's not longitudinal, just looking at what's happening at one particular time. If you look at it at 6 months, you can argue that it's also exchangeable because at 6 months you're not talking about correlate. But if you're talking about the combined year, 6 months and 1 year, well, maybe there's 2 things going on. Maybe there's an unstructured, maybe there's a exchangeable part and an autoregressive part that you want to consider. Well, that's sort of the idea behind this direct product that allows you to consider 2 ways to go, two possible sources of how you get your correlation structure. Now, I'm not going to go into it. I'm just telling you that's something that you might want to look at in your project if you have something like that. Most people didn't have that in the last few years. But if you have that, that's why that thing is there. To consider a more complicated situation where you have a more complicated structure where you have some part of it's longitudinal and some part of it's cross-sectional. Okay, that's why I'm telling you about it. So this is a table that gives you some choices, and then it even shows you if you go further in this table, it shows you what for example, compound symmetry looks like this. Unstructured looks like this. All the unstructured covariance matrix, all the variances and the covariances are all different. So it gives you first order autoregressive looks like this. The first order autoregressive, this part of it is the correlation structure. When you multiply it by sigma square, you're getting the covariance structure. Correlations are rho square, rho cubed. Okay. Now you notice toplets. Notice toplets. Just show you toplets. See toplets, sigma squares, sigma. In fact, I'm going to show you one other one. Toplets with. You see where it says toplets with 2 bands. Okay. Now look at this. This toplets with 2 bands. Okay. This says it allows for the variances. The variances are the same, right? Now, what is it saying about the covariances? It says, see, the covariance is sigma 1. The covariance between the first and the second observation is sigma 1. What's the covariance between the first and the second and the third? It's also sigma 1. Between the third and the fourth, it's also sigma 1. So what this is saying is if you're 1 unit apart, the covariance is the same. That's what it's saying. Just like when you're looking at AR1, if you're 1 unit apart, the correlation's the same. Rho, rho, rho. Rho, 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 you both. Okay. So But what about if you're talking about the correlation or the covariance between an observation that's the first observation and the third observation? What are you assuming? In this toplets with two bands. See the 0? And what about the first and the third? It's also 0. So what's the difference between this toplets two bands and the AR1? What's sort of a part of a difference? Okay. With AR1, you're assuming that there's a correlation between the first and the second. That's the same between the second and the third and the fourth. If you're talking about a correlation between the first and the third, are you assuming that it's 0? Go back to this. Are you assuming that it's 0? Look at this picture. It's rho square, right? Now, if rho is some number between 0 and 1, what's rho square going to be? Smaller, right? What's rho cubed going to be? Smaller. So if rho is small, if you're dealing with the AR1 and the correlation's small, and you talk about what does this matrix look like with rho square, rho cubed, this will be rho, but these two numbers might be very close to 0. So it's almost like when you've got a very small correlation, this matrix, this kind of alternative covariance structure makes maybe more sense, because it's basically saying you don't have much once you go beyond pair observations that are adjacent apart. So this is an alternative structure. It says once you get beyond a certain point, in this case, once you get on adjacent pairs, correlation is essentially 0, or the covariance is essentially 0. So we'll get back to toplets, but which is, and another word for that is stationary. But so that's something that a lot of people are using instead of autoregressive now, and we'll see. We'll go back to that later. So, okay, that's that. Okay. Now, last thing I want to do, and I'm not going to finish this, is I want to start talking about this. Is something that I've mentioned that I was putting off. So I hope this doesn't put you off too much. And then I'm going to talk a little bit about this and not finish it. Conditional linear models. I'll talk about conditional linear models. Okay. These are in the lecture material. So, and this is the slideshow called 04 with 0 conditional linear models. And there's a second one there with some output, computer output. So what do we mean when we talk about conditional linear models? Remember we talked about marginal, random effects, and conditional. How does conditional differ from the other two? Just roughly. Conditional will involve what? How's it different? It would involve an earlier value of the outcome as one of the predictors. That's what the conditional model is. Okay? Now let's look at two conditional models. There are actually two general forms, and I'm going to just look at it for, and actually these are not the most general form, but they're in a sense an illustration of what the general forms are. For a linear model, okay? Now what you're doing is you're predicting a y as a function of a bunch of predictors that are called x's, and you're also putting in the model an earlier value of y. That's what you're doing. Now, what earlier value of y is going into this model? The immediately preceding one. If it says I, j minus 1, if j is 3, what do if you're talking about the fourth subject and the third observation on the fourth subject, what's I, j minus 1? The second observation on the I subject. So yi, j minus 1 is the immediately preceding one. Okay? So this model only includes the immediately preceding y in the model, okay? As does this, but these two models are different. These two models are different, okay? Which I need to explain. But more generally, if you're talking about a conditional model and somebody has 10 observations, you don't have to, and you're doing a conditional model, it could not only be the immediately preceding one, it could be the one prior to that. It could be 2 observations preceding the third one or the 10th one. It could be the 10th one, the 9th, and the 8th. The 7th one, the 6th, and the 5th. So more generally, you can have more than the immediately preceding one in the model. It's more complicated. It can be more complicated. I'm just illustrating what happens if you only have the immediately preceding one. Okay, so this is one model, and this is the other model. Now, you notice I said j equal to or greater than 2. Why did I do that? Well, you notice the model has the immediately preceding one. Why did I put j greater than or equal to 2? Why don't I have j equal to 1? Because there's no previous one. So the first one, what's the value that I put in for the immediately preceding one to the first one? The first one was the first one. I don't have an immediately preceding thing. Started with this person. So I got sort of a problem. In fact, when I run this model and I want to consider the fact that I've started with a data set where I do have observations on the first person, I want to somehow include them in the model. When I start talking about the immediately preceding one, what do I do for the first person? What do I put for that person's outcome? Well, they're actually, for both these forms, as I'm saying, yj minus 1 is missing for the first time point. Two ways to consider this, the people who consider this, is they just say, okay, it's missing. I'm not going to count, I'm not going to put in something for the first person. The other way is I'm actually going to putting in that the first observation is 0. Neither one of them are great because neither one of them give you you don't have anything for the first one. To say it's missing is maybe that's better because you're not sort of counting it, but you'd rather have something for an early one if you can, but you don't have it. Okay. So that's one of the issues with this thing. But the other issue with this thing is look at these two models. What's the difference between this part of the right-hand side of both models? The right-hand side of this model just has the immediately preceding value, right? This has the immediately preceding value minus, what's this? What is this? Well, it turns out what this is the predicted value for the immediately preceding. This is the immediately preceding outcome. And this is the expected value or the predicted value for the immediately preceding outcome. Because it says xij minus 1 times beta. So that's what's in here. So if you think about the immediately preceding one minus what the model is predicting for the immediately preceding one, you're talking about a residual, aren't you? The y minus what it's being predicted for the immediately preceding. You're talking about a residual. It's like an error term. Okay. Now, if you're putting this error term in here, you can also write the model. You can also write the model like that. I'm replacing x prime beta with just saying the immediately preceding predictor value for y. But if I write the model not just as the expected value, if I write it as the outcome itself, I got this and I got that. I got two terms in the model that are error terms. Now, if this is my model, and I wanted to say, well, what's the expected value of y? What's the average y for this model? What's going to drop out? The expected value. What's going to drop out? Well, you know when you put the expected value of the error term, what's that always? It's always 0. What do you think the expected value of this term would make sense to be? This is a residual term. This should also be 0. So when you use this model, what you're basically saying is that the average value for this model, where I'm using this residual, is actually just the part of the model that relates to the fixed effects and doesn't include the variable that I'm putting in the immediately preceding value. And for linear models, this is the way it's usually done. You're usually putting in this linear thing, this residual term in there. But it's not the only way to do it. Another way of doing it is say, well, look, let's forget about this residual. Let's just put in the immediately preceding value and just run that model. Okay. So there are two ways to do it, although the second approach is usually done if you're doing a nonlinear model. It's not usually done if you're using logistic regression for correlated data. This approach is usually used, and you almost don't want to use this approach for logistic regression because the model, you can't get the expected value that easily because it's not a linear model anymore. But anyhow, these are two different, and this is called the lagged residual model. and this is called the lagged outcome model. Why lagged? What do you mean by lagged? Well, what you're doing, lag is another way of saying, in each model, I am going to put in something that has to do with what previously happened. So I'm lagging to some previous result. That's why the word lag is. So in this model, I'm lagging the residual. In this model, I'm lagging the actual outcome. So these are two alternative ones. Okay. Now, typically, when you're running a conditional model, these are the two outcomes. These are the two versions of the model. But if you're doing a linear model, this is the one you typically want to do. Okay. Now, the thing about this model is typically what happens here is, I'm going to show you how it's done. Now, I'm going to show you how the computer will actually do this. Okay. Options for fitting linear conditional models. Okay. Now, one option is to use this lag residual model and fit that model that way. Another option is to use the lag outcome model. And a third option is to not to do any lag thing, just use a marginal AR1 model. Okay, 3 different options on what you can do. This is what's in the literature on how to fit a conditional model. There are 3 ways you can do it. One is a lagged residual, one is a lagged outcome, and the other is not even have a lag. Just assume the correlation structure is AR1 and assume that that's going to give you whatever you want. That's going to be the right way to answer your question. Okay. Now, the thing is, what I did with the FEV data and with other data sets, I took these data sets and I ran these 3 different things for these different data sets to see whether I get the same answer or not. And it turns out key issues, well, one issue is how to treat the first, how to treat the earlier the first value, that value time 1. But will you get the same results when you do these 3 things? And the answer is no, not necessarily. So which option is best? And it's not clear. Okay. So what I'm saying here is there are 3 options. I'm just starting, and this is the reason why I put this off, because there are 3 alternative ways to do this. And they won't necessarily get the same answer. But you can do each one of these ways if you think about how to do it. So what I've done here is I've now considered the FEV data set. I'm going to illustrate how to do the lagged residual, how to do the programming code. I'm going to show you the code. And then I'm going to stop. I'm not going to show you the output. I'm going to show you the code. So if you're talking about the lagged residual for the FEV data set. Now this is the FEV data set where when we talked about it, we didn't use a conditional model. We either used a marginal model or a random effects model, and the random effects model we used was the one which had those 2 random effects, including that Z term, for identifying people that were affected by the pollution, specific people. So in this case, I'm saying, well, suppose we want to consider a conditional model. Now, whether we do or not is an issue, whether we want to do it or not. But this would be what the conditional model would look like, the lagged residual. This would be the lagged outcome, and this would be the without the lag. You just fit this model, and you wouldn't have any lag term in here. So let's look at the code for what you would do. I'm going to see if I can walk through with how this code works to show you how you would actually do it. I don't actually, do I have the output? I don't have the output. I don't have the output. I have it on a second PowerPoint presentation. But look at the output. Okay, this is the FEV data. Look at the first part of this code that's in blue. What have I done here? It's got proc mixed. Remember, we had 2 locations. So if I want to do this and get the do a conditional model for each location separately, I'm going to do it by group. Okay, I don't really need to do that, but if I want to just focus on one group, I just focus on the data set for one group. But if I say by group, I'm doing this for each of the data sets. Then I say class, subject, week, model, FEV equal to week. So what are these two statements doing? What are these 2 statements doing? They're just running the FEV data set like we ran. What's the covariance structure? What's the covariance structure? Do you see a repeated statement? Do you see a random statement? You don't see either one. So what's being assumed? Independence. Okay, so I'm just trying to use independence to get a lag term. Is what I'm doing. Doing independence to get a lag term. So when I do this, and then I say, output equal PRED run. What's this doing? What's this output statement, out P, doing? It's giving the results of everything, including the predicted FEV score based on fitting this model for every person in the data set. So for every person in the data set, not only are we getting the predicted, the estimate betas, but I'm getting the predicted values of what the FEV predicted value is for everybody. So that's what this has done. I'm just running this model and getting the predicted values. If I want to do an analysis separately for each group, I would add by group. If I want to do it for each model separately, I would just use whatever data for the model. But anyhow, look at the second set of code. I say data FEVD2, new data name, set predicted. So I'm using this predicted result, the output that I got from the previous thing that I'm putting in by group. I'm doing this separately for the group. And then I have this EST2 equal FEV minus predicted. What's that? What have I just done? What is FEV minus predicted? What kind of a variable is that? It's the difference between FEV and what's predicted. The predicted FEV. So isn't that a residual? In other words, I'm defining a term, a variable, from the output, which is giving me residuals. For every FEV score, for every one of those 40 kids in each location, I'm getting the FEV score minus the predicted value of the FEV score that I got when I fit the model. That's what this is doing. Okay. Now I'm defining a variable that's a set of residuals, 40 residuals. Now what I'm going to do with that is I'm going to define another variable. I'm going to find another variable which is going to be called the lag residual. And the way you do that is you say lag1 EST2. Lag1 EST2. EST2 is the residuals. And I'm saying create a new variable that's a bunch of variables that lag, that give me the immediately preceding residual for every person in every person's outcome. And then I'm not quite finished because the other thing I did, you see where it said lag underscore EST2 equal to dot? What this does is drop the first observation. If I wanted to use the first observation as 0, I'd replace this with a 0. But once I've done this, the key then next step is this, the last thing, number 3. Now look at the last thing. Look, it says proc mix by group class week model FEV week lag EST2 S run. What's this model have? What's in this model? What variables are in this model? What are the predictors in this model? One of the predictors is defined by the week term, right? It's 4 dummy variables for the 5 weeks and a constant, right? So what's this? This is the lag variable that I define here, which has the earlier value corresponding to the FEV score at each week. Okay, so this, when I run this, that's the conditional model. So what I'm doing is, and that's how you do it. You have to first run the model to get residuals, then you have to define this lag term, then you have to put it in the model. And when you put it in the model, you're doing a conditional model. That's how you do it. Now, if you weren't using a residual, you wouldn't have, you wouldn't have a FEV minus predicted. You just have predicted in there. But that's another story. I'm really, right now, I'm just talking about the linear model. So this is sort of how you do it. And that's all I'm going to do today because I think it's probably enough to be said at this point how you do it as far as the way the code works. But I do want to say a couple of other things now. Couple of things here. These are the 3 options, 3 ways you can do it, and the way I just described was how to do the lag residuals. Okay. Now, when I was doing it with the FEV data set, the FEV data set for each group was just made up data. So I had 40 kids in each of 2 locations, and I had their outcomes and I had their week scores. Okay. Did I set up the data set so that I'm setting it up so there's several observations on each person. But did I set it up so that the correlation structure was AR1? Did I actually make I didn't include that when I made up the data set. When I made up the data set, I just came up with some numbers to make it so that the first week the FEV scores were high and then they dropped down for the other weeks. But I didn't actually go about trying to make the actual correlation structure AR1. Okay. So one question you might have is if you're dealing with a data set where the correlation structure is not necessarily AR1, and you try these three things, these three different approaches to it, or these, wherever I have it here, these three approaches, maybe you won't get the same answer because the original data set's not AR1. But I wonder what would happen if you actually had developed the thing and defined the thing where the data set was AR1. Would you get the same answer? And I actually, with working with Mitch Klein, my colleague here, we actually developed a variation or simulated some AR1 data to see whether that would make a difference, and it still doesn't make a difference. So that's an issue. Okay. So there are several things, but it's not likely for FEV data. Will the lag residual conditional model give the same results as obtained from the marginal AR1 model? The answer is not necessarily, whether it's AR1 or not. Okay. Now here's the last thing I want to show you, which introduces a whole complication. Suppose you have this situation. Just look at this situation. You want to assess the effect of an exposure, that's your X variable, on an outcome Y, given that you know the previous outcome. So you want to consider a previous outcome and looking at, but your main goal is E on D, and you got a previous outcome, but the goal is there a relationship between E and D? Okay. And let's say D is blood glucose level in type 2 diabetes patients. So you have type 2 diabetes patient. And X, the X variable, is physical activity level from one time to the next. And you're looking at their blood glucose level and their physical activity at one time, the next time, and so on. And the goal is there a relationship between physical activity, how much physical activity they do, and blood glucose level? Okay. That's the question. So if that was your question, would you want to put in a model that considered the earlier value of Y in the model to look at the goal is the relationship between X and Y. You want to put an earlier value in there. Now I say, suppose that subjects with elevated blood glucose levels at time t, at time j minus 1, subsequently increase their level of physical activity, while subjects with non-elevated glucose level at time continue at the same time to maintain their usual level of physical activity. Then should I use a conditional model? Now this is complicated. Okay. Problem is when I look at the picture for what I'm describing, this is the DAG for this situation. This is where I'm going to stop because it's loaded with this. If I look at this DAG, now you notice I've got these two variables. X is physical activity, Y is blood glucose level. We're measuring both at different times. Physical activity at time 0, blood glucose at time 0, physical activity at time 1. And we want to eventually predict blood glucose at time 2 from physical activity level at time 1 or 2. Okay. Now it turns out that if we actually draw the DAG and consider what we have, this DAG indicates that the blood glucose is both a confounder and an intervening variable. Does it or does it not? How is it a confounder? How can you see that when you look at this DAG, blood glucose is a confounder between physical activity and, in other words, the immediately preceding value, Y1, is a confounder between physical activity level and blood glucose level at time 2. How can you see that? Because this is like C to E and C to D. So this is a confounder. Is it also an intervening variable relating physical activity to blood glucose? Well, not this physical activity, but this one, the early one. So there's an intervening variable in here. So one of the problems is if I use this model, if I use this particular model and I say, well, I'm going to control for the earlier value. I'm going to control for the earlier value. If I do that, okay, I'm dealing with the confounding part, but I'm not dealing with the intervening variable part. And so the problem is, it's not an appropriate approach to use conditional analysis or conditional correlated analysis to do this, because whenever you have a situation where you've got an intervening variable, a variable that you're interested in as your preceding variable to be both a intervening and a confounder, you can maybe deal with the confounding part, but you're not, by controlling for it, you're not dealing with the intervening variable part of it. And so that's not the way you do the analysis, and there's a whole other approach called a marginal structural model approach that the only person that, the two people that teach that approach in this school are Mitch Klein in the course that he teaches for our PhD students. So only our PhD students will hear that. And the other person is Dana Flanders, if you're taking his course. And he only does it, I think, in the course he teaches for PhD students. So you know, what I'm trying to say is this thing gets complicated, is what I'm saying. So whether or not you use a conditional model and whether it makes sense or not, there's arguments here. There's arguments for whether you should or you shouldn't. Now, if it turns out you decide that what I'm assuming here doesn't hold, then I could use a conditional model, because I don't have this. I'm assuming the intervening variable thing doesn't hold, so I don't have this arrow going in here. If I can assume that, then I could use a conditional model. I'm sort of just talking here, but to trying to tell you that the issue about fitting conditional models is an open question. Really an open question. Nobody has really done a great job with this thing. And if you actually call SAS and try to ask them to tell you how to do it, I'd like to see somebody do that, because they're never going to explain it to you very well. And it's not clearly written in the SAS package how to do it. So I'm going to stop with that. That's enough to be said about it. So there is this thing called the conditional model. There are ways to do it. I have some, in the second PowerPoint presentation on this thing, I actually show some output using this thing, but I'm telling you, the message is it's really unclear. So that's all I'm going to say about it in this class, unless somebody else in the class is interested enough and wanted to follow up and talk to me more about it. Okay. So, okay, with that, I'm done. But we're not done, because we have a group that's going to talk about their project. So of all the things that I talked about today, some of which was really a mess and I didn't do a great job, some of which I did a better job, but maybe what Julia, Mohammed, and Key are going to do is going to be completely clear compared to what I've done. So come on, you guys, come on up here. And then next week, who do we have next week? We have somebody doing something next week. Somebody volunteered for next week. Yes. Okay, you guys are going to do it next week. Okay. So you're gonna conjure up your thing. Yeah. And you want me to turn off the recording? Sure. I'll turn off the recording, which I didn't turn off at the break, but let's see.